Today's panel promises to be an exciting one on the future of computing from some of the computer scientists that have influenced the state of computing that we know now, more than any other people. Today's panel will be moderated by Maria Klawe. Maria is president of Harvey Mudd College and the fifth president, and she began her tenure in 2006. She's a renowned computer scientist and scholar, and the first woman to lead the college since its founding. Her best-cited research works concern algorithms for solving genetic optimization problems, distributed leader election, the art gallery problem, and the effects of gender on electronic game playing, with some of the first works studying the differences between boys and girls and how they interact and socialize around video games. She also founded the Aphasia Project, a collaboration to study aphasia and develop cognitive aids from people suffering from it. She's a fellow of the American Academy of Arts and Sciences and the ACM, and is one of 10 members of the Microsoft board. I welcome her as moderator for today's panel.
It's a great pleasure to be here. I'm incredibly proud of what Microsoft Research in India has achieved in its first 5 years. And I want to just pass on my personal congratulations to Anandan, who is one of my favorite people in the universe, and who I think really had a vision of what research in computer science could bring to India and how it could really change things. We have a very distinguished set of panelists with us today. Each one is going to speak for 5 minutes on their vision of the future of computing and computer science. And I'm going to ask Sean to come back and he'll introduce each one briefly, and then they'll each speak briefly. And then, of course, the exciting part is I have some questions for them, but we're also looking forward to questions from the audience as well. Thank you.
So the first person up is Tony Hoare. Tony Hoare is the Corporate Vice President for External Research and Division at Microsoft. He leads the company's efforts to build long-term public-private partnerships and oversees Microsoft's research efforts to enhance the quality of higher education around the world. Before joining Microsoft, he served as the director of the UK's eScience Initiative. He also is a fellow at the UK Royal Academy of Engineering, holds a degree from Oxford, and also holds doctorate degrees in theoretical physics. Tony Hoare.
Thank you very much, Sean. It's an honor to be here and to be a member of such a distinguished panel. What I'm talking about for no more than 5 minutes, otherwise Maria will shoot me, is about the effect of computer science on science. So advances in computer science can really make a difference to the way scientists do their science. And what I'll be talking about is the changes in science caused by the amount of scientific data being generated. Jim Gray, one of our colleagues, who alas is no longer with us, called that the fourth paradigm of doing science. So what do I mean by the fourth paradigm? People have done scientific research experimentally for many hundreds of years, and since Isaac Newton and Galileo and people like Maxwell and Schrödinger, theoretical science has encapsulated many of these discoveries in laws of nature, which we summarize by mathematical equations. In the last 30 years or so, computational science has come into its own as a new methodology for doing science. People doing computational science need to know about algorithms, numerical methods, and parallel computers, and that's a new set of skills. But there's no other way that they can look at galaxy formation, that they can look at climate modeling and global warming and so on. It's not accessible to any other method. But what we're seeing now is a new generation of science, typified by, if you like, the high-throughput genomic experiments, which are going to be able to sequence the human genome of everybody on the planet for very cheaply in a very short time. And this is a huge amount of data. It's not just from biology, but it's also from satellites, it's also from new accelerators and sensor networks being deployed, for example, in mountains or in forests. So to do analysis of that, scientists need to have new technologies to know about data mining, data visualization, and data archiving, and understanding new techniques about databases which they haven't been exposed to. And that is an opportunity for computer science and for the IT companies to make a real difference to science. On the right of this slide, you can see the the astronomers are already putting all their data from different wavelengths of the sky into a huge, if you like, distributed database around the world, which you can then visualize. This visualization is done using Worldwide Telescope from Microsoft. And so computer science can help science move from data to information to knowledge, and that's really one of the major achievements. So reducing time to insight for scientists using computer science is the goal, and I'll show you one example of that in my 5 minutes. And what we'd like to do, and what I believe computer science and IT companies can do, is help scientists spend less time doing the low-level, boring, tedious bits of moving data around, combining it, and so on, and enable them to spend more time on their research. So this is the example I want to show. It's an example using advanced machine learning techniques to analyze the DNA of HIV sufferers. And this is a tool that's had great impact in this particular community. Large numbers of researchers in the HIV and hepatitis C communities are actively using it. And it involves a large amount of computation on the data. So up to millions of jobs. Some of the jobs require thousands of hours. And what we've been doing up to now is inviting researchers to send the data to Microsoft where we would analyze it for them. Well, again, using a computer science technology, we've replaced the researchers at Microsoft who did the analysis by putting the service up in the cloud. So we now have a cloud version of this that researchers can upload their data, do the analysis on these virtualized machines in the cloud, and get the results back. So that's an example, a practical example of computer science and IT helping scientists do their work. And in the future, what we see is that science is going to be a huge network of distributed databases which you want to add to and combine in all sorts of different ways, and add semantic information. So semantic knowledge like paper X is about star Y are the beginnings of a semantic infrastructure for doing science. And you'll combine the analysis of that by doing some of it on your desktop or your home computers or whatever, but also you'll have some services up in the cloud. So I think it's a very exciting opportunity for computer science and IT companies to really help scientists solve some of the problems facing the world today in the environment, in healthcare, and generally helping humanity. Thank you very much.
Thank you, Tony. Next up, we've got Professor Barbara Liskov. Barbara received the Turing Award from the ACM, and the Turing Award is computer science's highest honor, for her work in designing computer languages and software technologies that led to the development of object-oriented programming. Specifically, Liskov developed two programming languages, one in the 70s called CLU, and another Argus in the 80s. The ACM specifically cited her contributions to the practical and theoretical foundations of the programming language and system design. She's also the Ford Professor of Electrical Engineering at MIT, and we welcome her as a panelist today.
Okay, thanks for the introduction. I want to speak just briefly about the future of computing and computer science. As I'm sure you're all aware, computer science used to be a sort of a discipline where we worked in our systems and our algorithms, and maybe other people took advantage of this to run their applications on top of our machines. But today, we can see that increasingly computer science is everywhere, and it's increasingly interdisciplinary. You just heard in the previous talk some examples of this, computational science, computational biology, and so forth. But of course, that's not the whole story. Every discipline you look at today has an important computer science core, and computer scientists are in demand to work with people from other disciplines to help them develop the systems that they need. And I just mentioned a few other examples here, but you can just go on, including art and social science and so forth, human-centered medicine, where people will be having sensors on their bodies that will be able to alert medical personnel if there are issues, management of energy to try and reduce our use of energy, and so forth. However, the core of computer science still matters. It's not just a matter of working with scientists and other people in other disciplines. We need to continue to develop the core of computer science. And in fact, this is what computer scientists bring to the table. We bring to the table our knowledge of computer systems, protocols, algorithms, that's what we contribute to these projects. And so we have to understand what's going on in computer science. On this slide, I have just a couple of current computer science problems that I find extremely interesting. The first one is, how are we going to write the software that runs on the machines that are being developed today, the ones that have many hundreds or thousands of cores in them? And the problem here is how to write very large-scale parallel programs. Certain kinds of problems lend themselves to concurrency, ones where the different parallel threads don't have to interact very much with one another. But others have substantial issues when you try to parallelize them, because the different tasks that you can think of to run in parallel require interaction among the threads, and that can cause a huge loss of performance. Another problem that's going to happen in these machines is that you can't expect that all those cores are working all the time. And so you have to start thinking about how to run programs where the components of the programs may be failed, and you have to, in real time, start moving the parts of your program around. The other thing I'm very interested in right now is storage and computation in the cloud. I don't need to say very much about some of the problems there, because Adi Shamir in his talk pointed out to you the security issues that are going to result once we start to try and put computation in the cloud, and you can imagine the storage problems that happen also. These are problems where computer science expertise is needed today in order to make progress for the future. Now, I was asked by Maria to talk particularly about computer science education, and so I thought about what would I advise students who are trying to enter the field today. First of all, I would say to people that there's a great future for computer science. The people up on the stage, we had the benefit of getting into computer science when it was a brand new discipline. And so there was a lot of low-hanging fruit. We had the wonderful opportunity to help shape the field. But there's still a ton of things left to do. A lot of it has to do with moving into new disciplines and working with scientists. Some of it has to do with working in the core. Whatever we bring to the table, though, it's based on computer science. So the students of today need to have a very deep understanding of computer science issues, just like they have in the past. In addition, however, they need to have a strong background in math and science. At MIT, this has always been the case, and at many other technical universities. But the real point is that you don't know when you're a student where you're going to end up. And so you want to get as broad an education as you can so that in the future you can be agile. And since a lot of what we can see coming is going to involve interaction with other disciplines, you want to have that strong foundation so that you can move forward. You might also like to specialize in a discipline if you think I'm really going to go into computational biology, but you know the field's going to change, and so you may need to be able to change with it. And that's the end. Thank you.
Next up, I have the pleasure of introducing Butler Lamson. Butler was one of the founding members of Xerox PARC, where he worked and basically created the now famous memo, Why Alto? The Alto was later released in 1973 as the computer with the first 3-button mouse and a full-page monitor. It's really considered to be now the first canonical computer. Butler also helped create many other revolutionary technologies like the laser printer, the first WYSIWYG editor, and Ethernet. Butler also has the honor of having a unit of measure named after him, the mini Lamson, used to describe how fast people can talk. In 1992, he also won the Turing Award, and he's a fellow of the ACM and is now a researcher at Microsoft. We welcome Butler.
Thank you, Sean. I don't talk at anywhere near one Lamson anymore, but I'm not going to need to. I'm going to give you a complete survey of all of the past and future applications of computing. So computing started about 60 years ago, around 1950. And for about the first 30 years that we had computers, basically we used them to simulate things. And whether you simulated nuclear weapons or payrolls, the idea was the same. You build some sort of model of the world in the computer, you run it, and you hope that the results will tell you something interesting about what happened in the world or what is going to happen in the world. And this was enormously successful, and it continues to be enormously successful. And nowadays we model stars and we model protein folding and all kinds of wonderful things. Around 1980, though, another major application area for computing started to become important, and that was using computers for communication. And this has, and I mean communication broadly conceived. It includes, for instance, storage, which is a way of communicating from the present to the future. And this has brought us the internet and email and Google and all kinds of other wonderful things, Twitter and all kinds of other wonderful things. And it's been hugely successful and greatly expanded the scope of applications of computing and their effect on daily life. And this, again, this too, like simulation, is certainly going to continue. There are many, many exciting opportunities in the domains of both simulation and communication that haven't yet been explored. But it's been another 30 years, and I think it's time for another great wave of applications of computing. And to these, I have given the name embodiment. And literally, embodiment means putting into a body. And what I mean by it is non-trivial interactions between computers and the physical world. The National Science Foundation has given this subject the unlovely name of cyber-physical systems, a term that only a bureaucrat could love. And this area has enormous scope, and I think that it's going to be the hottest area in computing in the next 30 years. The most obvious manifestation of embodiment is robotics. For about 25 years, I've been predicting that the next decade would be the decade of the household robot. And until very recently, this has been a complete bust. But we now actually have a household robot in the form of the Roomba vacuum cleaner, of which several million have been sold. So there's hope. We also have a very exciting application of robotics is cars that can drive themselves. And we have an impressive demonstration that hints at the possibilities for this in the DARPA Urban Challenge that took place a year ago, where they had a number of completely autonomous cars driving around a small town for several hours, really quite successfully. I think that we are probably 15 years or so from the time when this can be deployed on a large scale, but the benefits should be completely obvious. I describe it actually under the rubric of a grand challenge for computing is to reduce highway traffic deaths to 0. And that can only be done if the cars drive themselves, at least in emergencies. Other applications of embodied computing, of course, are sensor networks and all kinds of prostheses of various kinds. The prosthesis that I want, which I think I'm probably 3 or 4 or 5 years away from having, is one that can tell. I have a terrible memory for people's names and faces. So the prosthesis I want is one that can tell me when I walk up to someone. If I don't immediately say, "Hi, Rick," it's going to whisper in my ear, "That's Rick Rashin, and he's the head of Microsoft Research." This would transform my life. Other people have mentioned the widespread networks of sensors, the effect of which is to couple the world of computing much more tightly to the physical world. And there's just innumerable other potential applications for moving in this direction of non-trivial interactions between computing and the world. So if you're looking for something really, really exciting, it's not the greatest way to get a job in the next year, but looking into the future, I think this is going to be the most exciting area of applications of computing. Thank you.
Finally, we have Tony Hoare. After a short stint in the UK Navy and as a graduate student then at Moscow State University, Tony studied machine translation in 1959 and is one of the earliest computer scientists that we have here with us today. While there, basically, in order to look up an efficient dictionary, look up words efficiently from a dictionary, he invented one of the most well-known sorting algorithms that virtually every computer science student has studied, at least in the first couple years, is quicksort. Tony is also a Turing Award winner, and will be talking today to us about the philosophy of computer science.
Thank you very much. I want to talk in my brief 5 minutes about 6 philosophers. The first one is me, so I don't need to say very much about myself, because you can read read more in this lovely notebook that Microsoft has given us. The second one that I would like to mention, the first in time, was the great Sanskrit grammarian and scholar Panini, who in the 6th century BC, you probably know much better than I and far more about it than I do, investigated the syntax and semantics of the classical language Sanskrit. He was interested, like many philosophers, in the phenomenon of language, the structure of language, and the way in which language is built, and the way in which it conveys information. And he encapsulated the rules of the formation of sentences in a syntax, including, I'm told, some 4,000 rules governing the syntax of Sanskrit. Computers have revolutionized the study of syntax, but Panini's ideas and his rules, I'm told, are the basis of what is now the thriving research area, and perhaps soon to be in widespread application, the area of machine translation of languages, which formed my own introduction to computer science. The next great philosopher that I heard of was Aristotle, and Aristotle, of course, was the founder of nearly all the sciences that we know today: biology and physics and astronomy, meteorology. And I would like to identify him as a fellow creature and a fellow computer scientist because of his passion for classification and understanding and modeling, and in particular for his work on logic. Aristotle was interested in argumentation and convincing people of truth. He found that his rivals were constantly using false arguments, and so he devised a logical system known as the syllogism, which would enable people to determine whether an argument was correct and valid, or whether it had a flaw in it. Logic is now, as you know, the basis of the very hardware of our computers, and the kind of logic that the idea that one could test the validity of human reasoning by application of mechanical rules it still remains the basis of our work in the understanding of computer programs, and indeed has remained a great influence on the whole of philosophy. The next philosopher, I'm only just picking out a few names that I know, is David Hume, the English empiricist philosopher, who was more interested in inductive logic than in deductive logic. The paradigm of inductive logic, very crudely, is that if you observe that all the swans that you have seen are white, then you infer inductively that indeed all swans that exist are white. Now, the ideas of inductive logic, of obtaining knowledge by generalization from the real world, are now the basis of the machine learning algorithms that are finding widespread application in the use of computing. Going back to the deductive logic, I'd like to mention the work of Leibniz, a German philosopher, and the inventor of early calculating machines. They were made of brass rather than silicon. He had the idea that, similar to Aristotle's, that the validity of mathematical arguments could also be tested by a purely mechanical process, which he formalized in his rule of equality, for example. So that he felt that mathematicians should be able to resolve all their disputes by just calculating whether their reasoning was correct. So he was the first person who realized that computers could engage in deductive logical reasoning. Bertrand Russell, the English philosopher of the last century, was the person who first attracted me to the study of philosophy. His greatest work was in the foundations of mathematics, the discovery of the basic principles which underlie all mathematical arguments. His ideas and his methods have now been incorporated into sophisticated mathematical proving systems, which have proved serious, outstanding conjectures in mathematics, including the four-color theorem and probably the Kepler conjecture as well. His techniques and the techniques of the earlier philosophers in the study of logic are now helping to keep our computers free of viruses by checking the logic of the computer programs inside our computers to make sure they contain less vulnerability to external attack by hackers and malware. So, in summary, I believe that computing science will have not only an enormous effect on all other branches of science that Tony Hoare has alluded to, that they will certainly generalize their application from a pure calculation, as Butler Lampson pointed out, was the first use of computers, to communication and to data storage and memory. But I would look forward to the time when they could also give practical assistance to human reasoning, to the capacity that human beings have, which is not shared as far as we know with any other animal, to reason precisely and accurately about the world that surrounds us, whether that influence is by inductive logic or by deductive logic. The computers will offer us an aid. And so in the end, they will come to realize the prediction made by my friend E.W. Dijkstra, that computers would have more influence on the culture and understanding of the human race than they even do on our economic welfare and health and all the other applications to which computers have found ways of benefiting us. Thank you very much.
Well, I think you've seen a wonderful variety of views of the future of computing. And the thing that is so magical about computing and computer science is that it is all of these different possibilities. And, you know, sometimes I have run into people who've said the age of IT is over. It's absolutely wrong. The age of information technology, computing, and computer science is just beginning. And in the next 50 or 60 years, we're going to see, as you've heard described by our panelists, computer science and computing having an even greater impact on all aspects of our world. I'd like to encourage those of you in the audience to, if you have a question for one or more of our distinguished panelists, to please write it on a piece of paper and pass it out. I believe we have some people who are ready to pick them up over on this side. And so just raise your hand if you have written one. But I'm going to, while they are picking them up, I'm going to start out by asking our panelists each the same question. And Butler, you're going to answer it first. What's the one thing that scares you most about the future of computing? What could go wrong?
Well, I could sign up with Bill Joy and say that if we're going to have embodied computers, they might take over. I don't really see that there's any compelling reason to be extremely frightened of anything. I think that there'll be plenty of problems that we'll confront, but it's normal in the world to confront problems and have to deal with change. I don't really see anything to be extraordinarily worried about.
you can reinterpret this in terms of what's a major challenge facing the future of computing. Barbara?
Well, I guess the thing that scares me the most is actually automated warfare. Robotics has been, as Butler pointed out in his talk, coming along nicely, and we can see more and more powerful uses of robots in the future. But when we can fight wars where there's no human cost on the side of the aggressor, I worry very much about what the impact of that is going to be. I think what's really going on here is that we have new technology, and whenever there's new technology, it's very difficult for humans to catch up with that and figure out what's necessary to try and keep it in check. And I always worry that we might reach the point where the technology is beyond our ability to control. We can see those kinds of problems today with global warming, and so. But I'm not nearly as optimistic as Butler is.
Okay. Tony, do you have an opinion on this?
Which Tony?
Oh, sorry. Tony 1, Tony 2, Tony 1.
Yeah, well, I have, all my family use things like Facebook, and there's an interesting book by Gordon Bell called Total Recall. It's about the days where you will actually be able to remember everything, record everything in your life. And so I worry about not being allowed to forget embarrassing incidents, remove photographs that are out there on the web, and we all have those, I'm sure. And the other thing that is scary to me is privacy. And actually maintaining a balance between privacy and openness is a very difficult balancing act, and I think we have some way to go. And we're seeing this now in, with the latest issues between Google and China, for example. So many challenges, but overall I remain optimistic. I'm in Butler's camp.
And Tony 2.
Tony 2. Yes, I could say that I just agree with everything that's been said so far and don't have very much to add. What frightens me is what is called the digital divide, that the people who gain benefits from computers are rather few among the population of the whole world, and the people who gain no benefit from them have little reason to love us. So I think the challenge is to make computers relevant to all the people of the world, and maintain, not only for their own benefit, but also for everybody's benefit, because without the universal realization of the importance of computers, things can go wrong in so many different ways with our civilizations and with our computers. Yes, that's all I have to say. Thank you.
Tony number 2, you get the first question from the audience. Sir Tony Hoare, you picked only a few names, but how come Gödel does not figure in it?
Oh.
And what impact does this theorem have on the future of computing?
I was introduced to Gödel's theorem, or rather Turing's version of it, by my philosophy tutor at Oxford in the early 50s. And I've thought about it quite a lot ever since. The analogy that I would like to draw is that Gödel's theorem is an impossibility result. It tells us that there are limits to what computers can do, absolute limits that can never be passed. And there is an analogy here with other branches of science which are also based on impossibility theorems. The impossibility theorem of quantum physics, for example, the statement that you can never accurately measure both the position and the momentum of an elementary particle, has to be accepted by the physicist as an ultimate limitation to the accuracy of any measurement whatsoever. So I'm no more frightened of Gödel's theorem than the physicist is of quantum physics.
Thank you, Sir Tony. The next question from the audience was addressed to Professor Barbara Liskov, but I want the rest of you, particularly Butler and Tony Hay, to think about it as well. So, to Professor Barbara, is it possible to have an industry-ready graduate
Say that again?
Is it possible to have an industry-ready graduate, a graduate who is ready to go directly into industry? And I would actually perhaps paraphrase this as, what is an industry-ready graduate?
So my position on this is that the goal of a computer science education is not to produce an industry-ready graduate. Rather, it is to produce somebody who, with a little training in the exact tools that are being used in the company they're joining and some knowledge about what that company is interested in, will be able to do useful work for that company. And the best way to educate them is to provide them with the basics and the methods of reasoning that will allow them to adapt to whatever the requirements are. You know, those of us in academia for years, for example, have been asked, please prepare people who can write programs in C or whatever the popular language of the moment is. This is absolutely not what we should be doing, because we need people who are able to change and adapt, and your careers just evolve, and you have to be able to move with that.
Yes, I agree with that, thank you, but let me ask Butler to see what he thinks.
I agree completely with Barbara, and another way to say that is that, of course, it's possible to have an industry-ready graduate, and that may be very good for the company that hires that graduate for the first year. It's not especially good for that company 5 years down the road, and it's certainly a terrible thing for the graduate, who will find himself or herself obsoleted within a fairly short time. So don't go down that path.
Well, I take a slightly different view. All right?
Go for it, Tony.
I mean, I used to be head of a computer science department, and we all write in computer science departments software as experiments and prototypes. And I actually don't think necessarily that all our students are the best at writing software and doing the testing and the specification and so on. And I do think it's possible to teach students better software engineering, and I think this is very important. I think you teach the principles of it, but teaching, for example, how to program securely with some understanding of possible threats, if some malicious person picks up your code and does things with it, I think we can do a much better job. And I agree, I think, with Tony on my left, that formal methods and verification, they're always going to deliver, but I think they are going to deliver in the next 5 to 10 years. So I find myself thinking that we can do a much better job in academic computer science departments in teaching people how to write better and correct software.
Tony, too.
Thank you. I think it is possible to produce an industry-ready graduate, but just that industry isn't ready for him or her yet.
Okay, in a different, direction, this one, I'm going to allow whoever wants to answer this. What suggestion would you give to a student pursuing a career in computer science, especially, and you can do that, the broad answer, but the particular person wrote, especially in the research field of data mining? Okay, I'm going to answer this one. I think the very first thing about computer science is that it's an area in which you have to keep on learning for your entire life. Because computer science, it's still in that part of the curve where it's evolving very fast. And I think data mining is a great example of a part of computer science that has really come into its own over the last decade, but I would say, like computer science itself, is still in very early stages of the kind of impact that's going to have. So the absolutely number one thing I would say to any students, raise your hand if you're a student here. Yes, we have quite a few. Never stop learning. Expect that no matter how great the institution you're at when you do your undergraduate degree or your PhD, for the rest of your career, you're going to have to learn. Now, lots of different ways to learn. Learn from your colleagues, learn from books, learn from lectures that you go to, but you're going to have to keep on learning. The second thing is you never know too much mathematics. I mean, and this actually addresses one of the other questions.
Could I just say something? I absolutely agree about it's important to know as much mathematics as possible. But I just want to ask Barbara, it was reputed that MIT didn't have a course on databases until very, very recently. Is this true?
This is correct. Yes.
So I think a course on databases is a good start.
Yeah, but let me actually, right.
All right, let me turn this over to Barbara.
No, it's okay.
Yeah, it's okay.
Okay.
Actually, I was going to say something completely different, which was you should watch out for over-specialization. I mean, you have to be specialized in order to get a degree, but it's not realistic to think that you're necessarily going to stay in the same area through the course of your career. So data mining might be a hot topic right now. It's not clear that 10 years from now you wouldn't like to be in a very different area of computer science. You need to be prepared for that. Of course, mathematics is a very good way to be agile within the computer science discipline.
Absolutely. Let me go for it, Tony, too.
Right. I think Anandan has already given the essential message to any aspiring computer researcher: have fun.
Absolutely.
I completely agree with that. So this leads me actually to another question from our audience. How to promote maths among computer science students? Industry does not seem to promote it. It is more programming focused.
Well, I've had this problem and I haven't found a solution for it yet, I'm afraid. The only consolation I have is the discovery that all engineers and most scientists also hate math. But they do it.
What?
Yeah, what?
Okay,
Yes.
raise your hand if you love mathematics here. Thank you. I'm going to close the panel session by asking each one of the panelists to respond to this question from a member of the audience, if you so choose. And the question is, what is the one thing which would revolutionize computing in the coming decades?
P equals NP.
Okay, that's a good one. Anyone not know what P equals NP means? Oh, this is a very educated audience. That's amazing.
I think one of the revolutions will be, one of the things I talked about, the genetic revolution. There'll be so much genetic data and analysis of people's genes that actually will become the province of computer science. And I think machine learning techniques will have a huge impact in genetic analysis, and you'll see personalized medicines where, I mean, there's some statistic that of the cancer drugs that are prescribed, only 25% have any effect, because it depends on your particular genetic profile. So you can see that has the potential to revolutionize medicine. Drugs that have been taken off the list because they cause some side effects may, in fact, be very good for certain subsections of the population with a particular genetic profile. And so I think that's the major transformation of medicine by computing.
Tony, too?
I think the transformation is already in good progress. Mobile phones. These are the things that bring computing to the masses. I don't know how they'll develop. I'm never able to predict what the next magic thing is going to be, except possibly it usually comes from Apple. But she said she was going to hit me.
I was just waiting for the appropriate moment.
Yeah. So I just want to point out that Butler interpreted the question the way I did, which is what's going to transform computing. And you two interpreted it differently, which is how is computing going to transform everything else.
That was because I couldn't top P equals NP.
Yeah. And I think, computing is transforming our society and will transform our society in miraculous ways, and we can see them coming. It's much harder to answer the question. I believe, what will transform computing. And the only other thing I can think of besides P equals NP is something like quantum computing becomes reality, and we have to start rethinking all the basic, science of computing. That would be a huge change. I don't actually think that's going to happen, but there certainly is a community that believes it will.
Thank you. Please join me in thanking our wonderful panelists.
Thank you, Tony.
You guys were fabulous.
Thanks very much, Mary. You did a great job.